Any questions about anything? Questions? Other than cupcake-related questions? Same as yesterday, pretty much. So, I mean, as long as it doesn't interfere with sleep, that's the key thing. You know. Yeah. Okay. Anything else? Any other questions? All right. So, remember last time we finished, or pretty much finished, talking about wavelets. Specifically, I'm trying an experiment here. HAR wavelets. And like I said, I've never tried to go over this stuff in class before. I don't know how it's been going. I've sort of made a lot of leaps in the math and said, it turns out this is true, it turns out that is true. And I'm going to give you a couple homework problems that I hope will give you a little bit of a feel for how to work with these things. So I think I'm pretty much going to stop there. I do want to mention just one little thing before we move on. I'm not going to go over the general concept of a multi-resolution analysis. I think I'll save that for a handout, which will become a monograph chapter at some point. And I'm not sure when you're going to get that handout, but it will come. So here's one final comment. Remember how I was sort of saying, I was trying to explain where we have this dot, 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 v sub minus 1 contained in v0, contained in v1, contained in v2, and so on. This sequence of subspaces of L2, and remember what v0 is. v0 is the set of all step functions that are constant on the intervals n to n plus 1. And for any k, vk is the set of step functions constant on every interval of the form L times 2 to the minus k up to L plus 1 times 2 to the minus k. And therefore, you can think of each vk as just being scale sub 2 to the k of v0. But anyway, we had that decomposition, and I was stating kind of loosely that the way you get from vk to vk plus 1 is throw in the wavelets of resolution k. All right? So in other words, to get from v0 to v1, you take all the wavelets psi sub n comma 0 and throw those in, and in addition to v0 gives you v1, and so on and so forth. And I was sort of dancing around that, verbally and all that kind of thing. Here's one sort of easy way to think of it. Okay. And it turns out that v sub k is equal to, well, I'm not going to write it this way. Well, yeah. Okay, I'll write it this way first. Span of the set of all wavelets of the form psi n comma L, where L is less than or equal to k. In the sense that the indicated set of wavelets the set of wavelets inside these parentheses is I need a longer piece of chalk for this, is a complete orthonormal set in VK. So, in other words, the set of all step functions constant on all those linear intervals, the set of all, in some sense, step functions of resolution k, is the span of all the wavelets of resolution less than or equal to k. That's all. Okay, yeah, Will.
But can't you have L strictly less than k?
Say that one more time.
Couldn't you have L strictly less than k? Such that L is strictly less than k?
Well, yeah, but this is the set of all psi sub n L's for all L's less than or equal to, Psi 0 gives you psi 1. So it's, yeah, L less, you're right, I'm sorry, L less than K. That's right. If you take V0, and then you take psi 0, and put that together with V0, it gives you V1. So it's all the resolution wavelets with resolution strictly less than K, taken together form an orthonormal basis for VK. Okay, so that's just another way of looking at it. And so that means that shows you how these wavelet bases for the VKs build up as K increases. Okay, so that's all. That's all I want to say about the wavelets. And, you know, I got a feel for how to go over this stuff. So you guys were the guinea pigs. I appreciate your indulgence. Any questions about this? And Zach, you missed the fast wavelet transform last time.
An hour ago.
Oh, cool. So do you understand why it's computationally good now? Like, sort of?
Sure, sort of.
Yeah. Yeah, basically you have this algorithm, you know, and you can decide ahead of time what resolution is going to capture most of the interesting features of the signals. But then after you do it, you can actually say, you know, I think there might be some higher resolution features of the signal around this time. So you can actually tweak it by just looking at the wavelets concentrated in that neighborhood of the signal of a slightly higher resolution. You know, it's a very flexible kind of technique to use to analyze signals, represent signals, whatever. And another thing is it generalizes beautifully to images, multidimensional signals, images and higher dimensional signals. Like, you know, there is actually a theory of Fourier transforms for images and higher dimensional objects. And this takes the place of that. It makes it much easier to analyze those things. So, whatever. It's good stuff. It's good stuff to know. And it's good stuff. And I got to say, though, that one of the reasons I wanted to go over it for so long is that it really does kind of use the full power of all the orthogonal expansion, complete orthonormal set, Hilbert space ideas that we talked about in the context of Fourier series. And in some sense, we went over Fourier series as an excuse to look at that stuff. Wavelets, you can't do without it, literally. All right, so moving right along. The next collection of topics, and this is going to link up a lot with what we did last spring, but it's in a little bit more rigorous way, a lot more rigorous way, actually. So next topics are the DTFT, the Discrete-Time Fourier Transform, sampling, interpolation, etc. Okay, and this is a really important circle of ideas. And so what I want to do is I want to start by talking about what the DTFT is, what the discrete-time Fourier transform is. And we did not go over this really in my version of 2200. Did they do it in the Dorshap version, the DTFT?
I think we breezed over it.
Breezed over it.
We didn't. I don't think we went too deep.
Okay.
It was a long time ago.
Like a year, right?
Yeah. It's a long time.
Well, wait till you're my age, and you know, a long time is when I was in school, you know, whatever. So anyway, okay. So what about the discrete-time Fourier transform, sampling, interpolation, etc.? The continuous time Fourier transform, we started off with that as a vehicle for understanding what frequency content means for an arbitrary continuous time signal. And so the background here is in continuous time, we've seen how, quote unquote, frequency content makes sense as a concept for either periodic signals, and that's the sort of the natural setting, but also for arbitrary signals, the ones that have continuous time Fourier transforms, like the finite duration A440. So periodic and other signals. So what sense can we make out of frequency concept in discrete time? It's hard, I think, to do that, honestly. It's hard, for me at least, to wrap my head around the idea of what is frequency in discrete time. So it's not obvious what that phrase, frequency content, means in discrete time. And in particular, we're not going to be looking at discrete time signals whose sequences of values are periodic. That's not really what that's not what frequency content is going to be about. You know, we're not going to really be looking at signals that go like 1, 2, 3, 2, 1, 2, 3, 2, and all that kind of thing. You know, it's something else. Okay, so just for the heck of argument, for the sake of argument, so let's consider, and say I'm given some little omega 0 bigger than 0, or actually it doesn't have to be bigger than 0. And as you recall, if you remember from ECE 2200, when we used that book, the discrete time omega variable was omega hat, little omega hat, and the continuous time omega variable was just plain little omega. In this class, the continuous time omega variable is capital omega, and in discrete time, it's little omega. So consider, given omega 0 in R, the signal x with specification x of n equals e to the j n omega 0 for all n in the integers. That's kind of like a discrete time version of e to the j omega 0 t in continuous time. We call this a discrete time sinusoid of frequency omega 0. So x is a discrete time complex exponential sinusoid of frequency omega 0. Now, frequency omega 0 doesn't mean that the values of x are an omega 0 periodic sequence of numbers. Omega 0 might not even be an integer, right? Or 1 over omega 0 might not even be an integer. But this frequency, the word frequency, comes in any event. Okay, so we think of this x as having frequency content at frequency omega 0. So we think of x as quote unquote having frequency content at frequency omega 0. Okay, fair enough. And that's sort of just like a, I don't know, government declaration, whatever. We declare that signal has frequency content at frequency omega 0. Now notice that if I shift omega 0 by any integer multiple of 2 pi, so note that if I, for any k in the integers, what happens if I take omega 0 and I shift it by k times 2 pi? Signal x also has specification x of n is equal to e to the j n omega 0 plus k2 pi for all n in the integers. And that's because e to the j n k2 pi is 1 for every n value, no matter what k is. This is the same signal x as that. What does this mean? One way to look at this is, that is to say, if x has frequency content at omega 0, so when x has frequency content at omega 0. X also has frequency content. And please let me know if you can't read what I'm writing on the board. It's between fingers, so it's hard to tell whether it's coming out right. At every frequency of the form omega 0 plus k times 2 pi for k in the integers. So pure discrete time sinusoids, if they have frequency content at some frequency, they have frequency content at every frequency you get by shifting that original frequency by an integer multiple of 2 pi. So we kind of expect that we won't be surprised, or at least I won't. See, because I know the end of the story already. So I can, this is the spoiler alert, whatever. We won't be surprised if we discover that for any discrete time signal x, so for any reasonable discrete time signal x, and so let's write it x in c to the z. Let's again assume, as we did for the continuous time Fourier transform, that all the signals are complex valued, but now we're talking about c to the z instead of c to the r. Any reasonable x in c to the z, x has frequency content that is 2 pi periodic in omega. And let's see how this arises. Okay, so it's time to sort of quit wringing your hands about what do we mean by frequency content in discrete time and define the discrete time Fourier transform. And the way we define the discrete time Fourier transform is an obvious continuous time version of the definition of the continuous time Fourier. There's an obvious discrete time version of that. So in sort of an obvious discrete time quote-unquote morph of equation script f in continuous time, we define for a given signal x in c to the z the discrete time Fourier transform also known as the DTFT of x by means of the formula x hat of little omega is going to be our discrete time frequency variable equals, and remember this is going to be an obvious discrete time morph of equation script f, so the integral in equation script f becomes a sum from n equals minus infinity to infinity, sum over all time, of x of n e to the minus j n omega. And that's for all omega in the real numbers. And to me, that's an obvious discrete time morph of equation script f. In continuous time, we had integral, instead of a sum, over all time, and time now is integers, of x of t e to the minus j omega t dt, and here n plays the role of t, little omega plays the role of capital omega, sum plays the role of integral, and there you go. And of course, this function of omega, this x hat of omega, is not always going to be well defined depending on the signal x. X has to have certain properties for that sum to converge. And so what we're going to do is we're going to formalize the definition the same way we did in continuous time as sort of a bilateral sort of thing. So obviously, clearly, x needs to have some properties. Or let's put it this way, the sum defining x hat of omega won't converge for arbitrary x. So we need to have some restrictions on x to make it happen. Okay, so more on that later. Observe, though, that if the sum does converge, what we've got there is essentially a Fourier series for the signal x hat of omega. Now wait, Fourier series are defined only for things that are 2 pi periodic. Why is x hat of omega 2 pi periodic? So observe, though, that if the sum converges for all omega, then x hat of omega plus any integer multiple of 2 pi, what happens when I plug omega plus k2 pi into that sum? I get the sum over n, x of n, e to the minus j n omega plus k2 pi, and e to the minus j n omega plus k2 pi is just e to the minus j n omega. And that is just x hat of omega. So x hat of omega plus k2 pi equals x hat of omega for all omega. Consequently, if the signal x has this DTFT and that sum converges for all omega, that function of omega is 2 pi periodic. And that's the thing I said that we wouldn't be surprised if we discovered. So thus, x hat is 2 pi periodic, has 2 pi as a period in omega, and if x hat indeed is going to represent the frequency content of the signal x, then the frequency content of the signal x, as we expected or at least wouldn't be surprised by, is 2 pi periodic. So thus, thinking of x hat as reflecting in a frequency content x of x, so x is frequency content, we're quote unquote not surprised. Okay, so anyway, so far that. Furthermore, the fact that x hat is 2 pi periodic and the fact that we've expanded it this way as the sum of constants times e to the minus j n omega, what that reveals is that these constants, these values of the signal x, are like Fourier coefficients for the 2 pi periodic function x hat of omega. So furthermore, the expression for x hat of omega in terms of x of n for n in the integers is just a Fourier series. It's essentially a Fourier series for the 2 pi periodic function x hat. And if you want to be specific about it, the nth Fourier coefficient of x hat is going to be x of minus n for all n. So specifically, the nth Fourier coefficient, say C sub n of x hat, will be x of minus n for all n in the integers. Why is that? That's because our Fourier series always had positive e to the j n omegas in the numerator, or e to the j k omega 0 t's in the numerator, and that's what we have there. We have a negative sign. And in any event, for every n in the integers, we're going to have the following formula. X of n is going to equal 1 over 2 pi integral from minus pi to pi of x hat of omega e to the positive j n omega d omega. And if you want, you could think of that as x of minus n is equal to e to the minus j minus n omega, and so on. Dead so. X hat is a function of a continuous variable omega, a continuous real variable omega. So x hat you can integrate. X you can only sum.
Makes sense.
Yep. And this is easy to show just by thinking of that thing as a Fourier series, or multiplying the series by e to the positive j n omega, and you find the one term left over, and so on. That's a formula that gives x of n in terms of x hat. Okay, so now I want to summarize this whole thing in the bilateral definition I promised you earlier today. So summarize as follows. Definition. A signal x in c to the z and a function x hat of omega that has 2 pi as a period are said to be a DTFT pair when either or both of the following equations holds. And the first equation is going to be the forward equation that gives you the DTFT in terms of the signal. That's the discrete time version of equation script f. And I'm going to call that unimaginatively equation DTFT is x hat of omega equals the sum over all n, x of n, e to the minus j n omega for all omega in the reals. And the other equation, equation DTFT inverse, blister. Okay, I can see I'm going to need some. Is x of n is equal to, okay, which is worse, the blister or the thumb? Now I know if I had my wallet with me, I'd have a Band-Aid, the whole bit. But you have a Band-Aid? Just, yeah, that would be awesome. Because we have like 11 minutes to go. Oh, thank you so much. I'll pay you back. It's brand name. No, actually, I use brand name Band-Aids because other ones suck, basically. Yeah, like, you know, Walmart brand. I mean, I don't go to Walmart, actually. It's like going to a foreign country where like, the water is dangerous to drink. I don't know. It's like, that's how I feel when I go to Walmart. I don't know why. Okay, now let's see if I can get this baby open here. I'll just tear across it. Yeah, I'm remembering back to when I had the cast on and I got blisters and I ended up putting like adhesive tape around my 2 fingers where I was holding the chalk, and that was a good thing. So that's probably what I'll do for tomorrow. But for now, I will finish this class. Ooh, and it's nice cloth like, you know. Good taste in Band-Aids. X of n equals 1 over 2 pi. Oh, that feels awesome. That feels great. And you know, the thing with blisters, if you get blisters, like when I played a lot of tennis, I used to get them on my feet all the time. Anyway, it's not pressure, it's abrasion that hurts blisters. Like I can press on this thing as hard as I want, it doesn't hurt, but as soon as I rub something on it, it hurts. Okay, so remember that. And so, oh well, let's not talk about blisters. Minus pi to pi, x hat of omega e to the positive j and omega d omega for all n. Integers. Okay, so that's what it means for signal x and a 2 pi periodic function x hat to be a DTFT pair. Okay, now we think, as in continuous time, of the DTFT as giving some kind of a representation of the frequency content of x, however you interpret that phrase. And as in continuous time, we want to extend the definition by linearity. And we also want to allow for deltas of various kinds. Okay, so first extension I want to talk about is the deltas. And if you recall from continuous time, I said we want to have deltas both in time and frequency, right? And we found that a delta in time went to a flat in frequency, and a flat in time went to a delta in frequency. And essentially the same thing is going to be true here, but the cool thing about discrete time is that the delta is an actual signal. It's not anything we have to sort of pretend about. Okay, so we want to extend. So we want to allow deltas in both time and frequency. And in discrete time, delta in time is a non-issue, so to speak, because it's an actual signal. What happens if we plug a delta in time into x hat of omega expression? So let x equal delta. Plug into equation DTFT. And what happens? You get x hat of omega equals the sum over all n delta of n e to the minus j n omega equals how many terms in an infinite sum are non-zero? 19? 1. Okay. And which one is it? Sorry? N equals 0. So it's equal to 0 plus 0 plus 0 plus 1 plus 0 plus 0. And this is the n equals 0 term. N equals 1 for all omega. So again, delta in time goes with a 1 in frequency, and 1, the constant function 1, is trivially periodic of every period. In particular, it is 2 pi periodic. Let's make sure equation DTFT inverse holds also for this example. So note that DTFT inverse also holds for this example. If I plug the constant function 1 into equation DTFT inverse, 1 times e to the j n omega d omega integrated from minus pi to pi and divided by 2 pi, what do I get? I get 1 over 2 pi, and there's two cases here. When n equals 0, I get 1 over 2 pi times 2 pi, because I'm integrating 1 from minus pi to pi, and that equals 1. And when n is not equal to 0, I get 1 over 2 pi jn times e to the j n pi minus e to the minus j n pi. And what's that equal to? It's equal to 0 because e to the j n pi and e to the minus j n pi are the same. They're both equal to minus 1 to the n. So this equals 0 when n is not equal to 0, and that's clearly equal to delta of n for all n. Okay, so bottom line, delta in time goes with constant in omega, just as in continuous time. And as in continuous time, we have a sort of a bilateral kind of notation to go along with our bilateral definition. So thus, delta of n goes with 1. That's the way people write it in a table of DTFTs. And what we really mean by this is the signal x with specification x of n equals delta of n for all n has DTFT x hat with specification x hat of omega equals 1 for all omega. Okay? Impulse in time goes with a flattened frequency. All right, what about impulses in frequency? What are they going to correspond with? Well, let's see. Let's figure that out. Like, I'm trying to think if I can do it in 2 minutes. So how about impulses in omega? Okay? So what if I have a signal, or not a signal, but a function, x hat of omega, with one or more impulses in it? So suppose x hat is a function that has, say, 2 pi, so has an impulse at omega equals, say, omega 0. What's going to be true for x hat to be a DTFT? For x hat to be a DTFT, it has to be 2 pi periodic. So for x hat to be a DTFT, x hat must be 2 pi periodic, and therefore it must have an impulse at every frequency of the form omega 0 plus k times 2 pi of the same weight as the impulse it has at omega 0. So it's going to have an impulse of the same weight at every frequency of the form omega 0 plus k 2 pi when k is in the integers. And if those are the only impulses in x, let's assume that's all of what all of x is. You're going to have x hat being an impulse train, as they call it. And, well, we'll see what happens next time. This class always seems so short on Wednesday. It's like, yeah.
What's like the intuition behind having like kicking the system in time and having a frequency going on like overall omega?
Well, remember that frequency content is not the response of the system to a kick. It's not the response of the system to a kick. It's not h. Well, we don't even have a system here. We're just right now, so far, we're just talking about signals, right?